Hi everyone, this lesson is going to be an example of using implicit differentiation to find the derivative of this formula. Now, this particular equation happens to describe this elliptical shape on the xy plane. It's very interesting. The diagram's just there to show you that this formula has some sort of a geometrical representation. Now, the task is implicit differentiation, or finding dy dx. And this is an implicit formula because we do not have y written as some sort of a formula involving x. And as a result of that, we can't use the usual derivative type rules. Now, I wouldn't even attempt to rearrange this to be y equals. There's a much easier way to go about this. And this is what we do. We literally take the derivative with respect to each of every term here. So let me write that. Derivative with respect to x of 5x squared minus, and I'll have derivative with respect to x of 3x multiplied by y plus derivative with respect to x of 2y squared equals derivative with respect to x of 6. So we've literally done the same process to every term. This first one doesn't present any challenge at all. 2 times 5 is 10, and reduce the power on x to 1. So that's 10x. I'll leave that next one for a minute. That's going to be a bit more interesting. Leave myself a nice big gap there to do that one. Then this one, this is implicit differentiation. Remember, when we do this, we're looking for a derivative of a variable y with respect to x. So we have to introduce dy dx, and then we multiply by the derivative of this term as if we were using y as the variable. So that's 4y. And derivative of a constant is 0. Now, what's going on in the middle? We need the derivative of a product. And that suggests that we should use our product rule. Our product rule tells me that we take the first term, 3x, and multiply by the derivative with respect to x of the second term, literally d over dx of y. Then we have the second term, y, and we multiply by the derivative with respect to x of the first term, d over dx, and the first term is 3x. All of that, it's subtract all of that. So here we have 10x. Now, what's our first term? Well, implicit differentiation of y. Derivative of y is 1, but remember we have to introduce the multiply by dy dx factor. It's literally the way it's written there. It is derivative with respect to x of y. It is dy dx. So this first part is minus 3x dy dx. Now don't forget to distribute that negative sign across, so it'll be minus. Now derivative of 3x is 3, and we still have the factor of y, plus dy dx multiplied by 4y equals 0. Now it's just a matter of collecting like terms. So what will I do? I'll move the negative 3y to the right hand side. I'll move the 10x to the right hand side. These two terms here that had dy dx, I will factor dy dx, and what will be left? Well, dy dx as a factor of this term would leave 4y, and dy dx as a factor of this term would leave negative 3x. And quickly enough, we will see that our derivative is 3y take 10x over 4y take 3x. That formula will give me the gradient of this curve. All I need to know is a particular coordinate, and I'll need to know both x as well as y. So if I, for instance, were to want to know the gradient at that point there, where x equals 0, I'll need to substitute x as 0 and solve this formula. Let's do that. So if we let x equals 0, my original formula would, well, the first term would be 0, the second term would be 0, I would have 2y squared equals 6. Divide through by 2, we'd have y squared equals 3, so y would be plus minus root 3. Now the positive and the negative gives me both of those. I'm only really interested in the point that I gave there, so that will be positive root 3. I'm going to be using the point, so I'm interested in the point where x equals 0 and y is positive root 3. The derivative then, dy dx. 3 times y, that's 3 root 3, minus 10 times 0 is nothing. 4 times y, that's 4 root 3. And again, 3 times x is nothing. The root 3's will obviously cancel, and I find that the gradient at the point of interest is 3 over 4. The gradient of the curve right there, and therefore also the gradient of a tangent line. If I was to sketch a tangent line there, I would find the gradient of that line is 3 over 4. So there we have it. That's implicit differentiation, and this one was slightly more interesting because the term here in the middle involved a product, and by using a product we had to do everything here. We had to use the product rule, and then implicit differentiation was just a little part inside the product rule. That's enough for this one. Thanks for watching. I'll see you next time.